Hi, my name is Stuart, and welcome to this series of videos concentrating on all aspects of electrical design relating to Chromatech multiviewers. We've been making multiviewers for the broadcast industry for over 20 years. These videos, I hope, will give viewers an insight into the design process, challenges, and compromises in the development of PCB assemblies required for Chromatech multiviewers. I'll try to provide viewers with interesting and entertaining content that should benefit students, electrical and CAD engineers, PCB developers, and just about anyone interested in the challenges associated with product development. I remember when I first started out as a young engineering graduate, probably on my first day, one of the older senior engineers walked over to me at my desk, and he said, "Son, I'll give you some advice. Engineering is 10% inspiration, 90% perspiration." You know, I'm not sure if he was trying to help me in my new career or give me advice to find a new one. But years later, his advice is self-evident. But I would add the caveat that the 10% inspiration is worth every last bit of the 90% perspiration. Well, that's enough reminiscing. Let's do some work. For schematic and PCB design, I'm going to use Altium Designer. But it doesn't matter which application you use, the principles are just the same, and I'll try to stick to good principles that are independent of the application. But since I'm starting a new project, then I'll briefly describe how I do this. I'm sure everyone has a different approach. I prefer to copy the project files from an existing project into a new folder and then rename the files. This way, all the schematic templates, libraries, project settings, PCB design rules, and other important documents such as bill of materials and PCB fabrication settings are all set up in just a few seconds. In this case, I just copied the project above. As you can see, the schematic and other project files are just the same. Before going any further, let's have a quick look at the SolidWorks model to get a better idea of how the card will be used and how this defines the PCB profile. Here I'm using eDrawings to view the 3D model that Spencer created earlier. This shows that we're going to design a rear interface card for a backplane. The plug-in cards can be seen when the lid is removed. Each plug-in card mates with a PCIe connector, so the plug-in cards have edge fingers. To keep things simple, I'm going to take the PCB profile from an existing card. The schematic files have been updated, as you can see in the project folder. Some of the sheets have been copied from existing projects, resulting in duplicated designators, which we'll need to sort out before annotating the design. We're also going to take any critical PCB designs and copy those to the new layout. So we need to make sure that the designators in the schematics match with those in the PCB. There are 4 schematic sheets that are associated with critical layout labelled as HDSDI out. I'm going to copy those from another PCB project, so I'll preserve those schematic designators and I'll reset the remainder. Let's just go ahead and validate the schematics. As expected, we have some duplicate designators, so we need to re-annotate the sheets where the designators are not being preserved. The process involves resetting the designators on all sheets except the HDSDI out sheets, and then re-annotating the entire project. Now, when the project is validated, we can see there are no errors resulting from duplicate designators. After tidying up the remaining single pin net errors, the project compiles successfully. Let's go ahead and review each schematic sheet, and I'll highlight anything interesting. The first sheet shows the edge finger connections. Here, there are some differential pairs and some power connections that have already been assigned net colours. Each differential pair is allocated a unique differential pair class name. They have their own class name even if they will share the same rule. This will make it easier to find them in the PCB layout. We'll assign a design rule later once the impedance profiles have been defined in the PCB. Pages 2 to 5 show the HDSDI cable drivers. The nets connecting the driver to the connector have a 75 ohm class assignment. On page 6, we see reference and timecode buffers. Page 7 shows the microcontroller. We use a microchip PIC 18. In this case, we're using an SO28 package. The preferred package would be TQFP, but these are still very difficult to find at the moment. Ethernet is used for external communication with the multiviewer. So this page shows an Ethernet connector with signal connections directly to the backplane. Internal communication uses CANBUS, which is a robust automotive standard. On page 8, we can see the hot swap controller. Rear cards can be hot swapped, so each rear has a hot swap controller mainly to limit the inrush current. On page 9, we can see the serial comms RS232, RS422 and RS485. An RJ45 connector is used to take advantage of Ethernet pairing for the balanced RS422 output. Page 10 shows the power supply circuit. Reliability of the power supply is a major requirement for multiviewers as they are in constant use. So we only use TI automotive grade components. The TPS 65261 is a triple output, non-isolated DC to DC switcher that has a small PCB footprint. This can also be configured to use fewer than 3 outputs if required, and for this design I'm only using 2 outputs. Pages 11 and 12 are documentation pages showing the comms pinouts. It's very convenient to be able to copy and paste images into the schematics for future reference. Page 13 shows an analog audio output. This is a line level output for monitoring purposes. Finally, on page 14, on this last sheet, there are 6 fiducial markers that will be used to locate the PCB during assembly. These are 1mm diameter pads, and 3 will be located on the top and 3 on the bottom. There is also a component with 2 connections to ground that correspond to through-hole pads. During assembly, a short wire will be soldered between the pads and used to provide a ground for a scope probe if required when fault finding. There is also a component that will represent the bare PCB to appear in the bill of materials. There's no need to generate a new PCB profile because we can use an existing PCB that has the same profile. It will also save time to retain some aspects of the layout that are common between the 2 designs. This is how the PCB looks after the non-overlapping components have been removed. The only components remaining are the hot swap controller, CANBUS, PIC 18 with its associated components, and the TPS 65261 power supply. After checking that the schematic designators match the retained PCB components, we can go ahead and update the PCB to match the netlist generated from the schematics. The ECN shows that there are a large number of components to be added. We'll go ahead and execute those changes. The new components are shown off-board, and the retained components and traces look good. The schematics and PCB are now synchronized. Remember I said that we would be reusing the HDSDI output sheets from another design. Well, it's time to copy and paste those blocks into the design. Group select the components and traces from the donor board. Make sure that all layers are turned on and everything is enabled in the selection filter. It doesn't matter if a few extra components are copied, as these will be cleaned up after the paste is completed. On the target board, make sure that the Paste on Current Layer checkbox is unchecked, otherwise the components and traces that have been copied will all end up on the current selected layer, which is layer 1 in this case. The paste looks good, so all that remains is to remove any additional components that were not required. After removing any components and traces that are unused and rearranging the connectors, the layout appears as shown. I've also added an Ethernet connector with its associated components from another donor board. Now that all donor components have been added to the PCB and the schematic designators have been changed to match, then it's time to synchronize the PCB once again to the schematics. We'll go ahead and execute the ECN. There are no errors, and we can see that the nets have been added to the components. The synchronized design is complete, but there's a problem. The connectors won't all fit on the board. There's simply not enough room. It was planned that this board would have a daughter card, and I'll post another video showing the daughter card later. But in the meantime, we need to make a decision on which connectors will remain in this PCB. It makes sense to move the comms RJ45 to the daughter board, as the data rate is much slower than the Ethernet RJ45. The remaining connectors fit comfortably along the edge of the PCB. A second consideration is to remove the signal crossover. It's better to move the Ethernet RJ45 and the audio connector to the right-hand side of the BNC group. Let's go ahead and delete the comms connector and all of its associated components. The audio connector will then move to the top of the board with the Ethernet RJ45 next to it. To keep the audio components and traces locked, we use the Group X move. The rear is 114.6mm and the draft placement is 108, plenty of room. The BNC group can now be moved to their correct location relative to the PCB edge. By referring to an existing PCB, we can see that the first connector is located at X equals 8.9mm and Y equals minus 2.1mm from the top corner of the PCB. On the target PCB, set the origin to the top corner of the PCB, and we should be able to move the entire group to the desired location. First, we need to identify the current location of the first connector. The X coordinate is 48mm and the Y coordinate is 110.626mm. So, shifting X by minus 39.1 and Y by minus 112.726mm will move the group to the correct location. The audio and the Ethernet connector have also been moved to their final location, so all components have now been placed. The middle of the board looks empty, but we are reserving that space for the high-speed differential pairs, which will have the highest priority. The crossovers on the differential pairs will also need to be addressed on the schematics before they can be tracked. An SMT socket has been added to the bottom of the board to allow signals to pass between this card and the daughter board. I've already moved the comms schematics to a new project that will become the daughter board, and I've added another sheet called Inter to this project. This has the SMT connector and signals. This board will have 6 layers, because reference ground is required beneath the differential pairs, and the high-speed differential pairs will only use top and bottom layers to avoid via stubs. The remaining 2 inner layers will be mostly used for power and any signals that cannot be located on the top or the bottom layers. The footprint of the TPS 65261 in the bottom right only uses 2 out of the 3 outputs, so it can be arranged to fit very nicely into the bottom corner. The audio DAC has a linear regulator supply located immediately above the TPS 65261. Let's now have a look at the layer stack manager. The layer build is symmetric and the dielectric thickness is checked for manufacturability using an online custom stack-up from one of the many fabricator websites. The overall PCB thickness is 1.6mm plus or minus 10%. This is a typical 6-layer stack-up that I use with microstrip differential pairs. Selecting the impedance tab shows that there are 4 definitions. The first definition is used where there is sufficient space to allow a wider tracking gap to be used. The dielectric spacing of 0.24mm on the outer layers assists in achieving 100 ohm impedance with a wide trace to reduce skin effect loss. A thinner dielectric would reduce the impedance and would result in a thinner track being used to bring the impedance back to 100 ohms. The second impedance definition is used where there is limited space, such as signals entering or leaving pins at an IC. The track width is smaller at only 0.2 of a millimeter, which increases the impedance. So the gap is reduced from 0.23 millimeter to 0.13 millimeter in order to reduce the impedance back to 100 ohms. The skin effect loss will be higher here, so the impedance definition is only used for short track runs. The third definition specifies the track width to achieve 75 ohms impedance. This works out at a track width of 0.19 millimeters, which is okay for short trace runs between the connector and the passive components at the driver IC. Finally, the fourth definition is used for strip line differential pairs on inner layers. This might have been applied to the slower differential pairs such as Ethernet. Now that the impedance profiles have been set in the PCB layer stack manager, it's time to update the schematics so that the rules are correctly applied to the traces. This can be done in the PCB, but I prefer that rules are defined in the schematics and passed to the PCB. On the first sheet, there are several differential classes. Inspecting the properties of the SDI out differential pair directive shows that a rule already exists for the differential pair from the previous layout. In order to select one of the available impedance profiles, it is necessary to select the current PCB layer stack from the drop-down list, and then check the Use Impedance Profile checkbox. The drop-down list below the checkbox then shows the available impedance profiles that were generated in the layer stack manager. I'll use the low-loss 0.3 mm track with 0.23 mm gap for the SDI out traces. The selection process is repeated for the other differential pairs. The other pairs, such as Ethernet and CANBUS, can use the impedance setting that has 0.23 mm track with 0.13 mm gap, as the skin effect loss will be much smaller for these. On sheet 2, the differential pair directive SDI out TX is used to control the short track between the AC coupling capacitors and the driver input. This can also be set to use the impedance profile with 0.23 mm track and 0.13 mm gap to make it easier to track into the IC pins. The 75 ohm directive is also shown on the same sheet for the traces between the cable driver IC and the connector. Check that the impedance rule is set to the 75 ohm rule defined in the layer stack manager. Once the directives have been updated on one of the sheets, then they can be copied to the remaining sheets to avoid having to edit each directive. Once the directives have been set on each sheet, then the project can be validated and the directives synchronized with the PCB. Selecting the PCB properties from the Panels tab and then selecting the differential pairs editor from the selection list will display the 4 differential pair classes. Selecting individual classes will highlight the nets or traces in the PCB. Before I can start tracing the differential pairs, I need to resolve the signal crossovers. The SDI signals are not dependent on signal polarity, so positive and negative inputs can be swapped to resolve intra-pair crossovers at the edge fingers. Crossovers between pairs will need to be resolved by changing the location of signals going to the edge fingers. The cross-reference feature combined with vertical split screen makes it easy to identify the nets in the PCB that correspond with the schematic. So the process to resolve the crossovers involves using a vertical split screen to view the schematic and PCB at the same time, and change the schematic assignments for each pair. Note that half of the differential pairs will be on the top side of the edge fingers, and half will be on the bottom side. So the allocation of pairs will alternate between top and bottom pads on the edge fingers. After validation, the PCB can then be updated. The changes all relate to differential pairs. When the PCB is updated, the intra-pair crossovers have been removed. Although it still looks as though there are crossovers between pairs, keep in mind that 4 pairs will be traced on the top of the edge fingers and 4 on the bottom, so there are no actual crossovers. With the crossovers removed, the differential traces can now be completed. When routing differential pairs, use strong glossing effort to ensure that the traces are optimized leaving pads. I find it easier to swap to the other end point when the trace is near to completion. This ensures that the traces are correctly routed as they enter or leave pads. Some other points to note is that the traces alternate between top and bottom layers, so I'll need to place ground vias close to the vias where the signals change from top to bottom layers. This will ensure that there is a route for the ground return current. I'm using a 0.1mm grid when routing these traces. Finally, the high-speed traces should be positioned to avoid each other and not routed close to any other components or traces. If you'll bear with me, I'll go ahead and complete the routing now and fast forward. The routing is almost complete, but the PCB report still shows that there are unrouted connections. The one shown here is pretty obvious, but sometimes, if the unrouted connections are short, then they can be difficult to spot. When this happens, I go to the Object Visibility and turn everything off with a single click. Any unrouted connections can then be spotted immediately. In this design, there is one long unroot and 3 small ones that would be difficult to spot otherwise. Now, when object visibility is restored, the unroots can be inspected and resolved. The routing is now complete, so let's take a moment to review the design and have a look at each of the layers. This is an opportunity to look for any problems that might affect fabrication or assembly of the PCB. The summary shows 0 unrouted connections, so let's go ahead and review the PCB layers. The top layer has copper pour, and I can see from the spacing between pads and copper pour that rules are being used to modify the default clearance on high-speed traces. Thermal reliefs are visible on through-hole pads. If this connector is to be hand-soldered, then the pads connected to ground on multiple layers will be more difficult to solder than the signal pads. Reducing the thermal spokes on all ground layers is one way to reduce this problem, or only connecting ground on some of the layers is another possibility. Layer 2 is a solid ground pour. This is to be used as a reference plane and ground return for all the topside tracking. Ground is poured up to 0.1mm from the PCB outline. Note, the ground pour does not extend under the edge fingers, as this is defined by the PCIe standards. The copper keep out for the edge fingers is defined in the edge fingers component. Layer 3 is a power plane layer. There are 3 planes shown here. Although the power nets could have been traced, I prefer to maximize copper pour, so the planes are convenient for this purpose. I'll add ground pour to the large area at the top of the PCB later. Note the anti-pad keep-outs in this layer that are located beneath component pads that are used with high-speed signals. Layer 4 is a solid 3.3 volt pour. Anti-pads are also present on this layer. Layer 5 is the ground reference layer for the bottom side tracking. Note, there are no anti-pads here, so this is also the ground reference for components on the top layer to reduce the parasitic capacitance of the pads. The bottom layer also has ground pour, with clearance rules defined for high-speed traces. I'll make a note to add copper keep out to prevent ground infill between the high-speed differential traces. Before making any further changes, let's run the design rule checker to see if there are other errors to be resolved. Even on a small board such as this, there are still nearly 200 errors. I can see the first large error is a clearance violation from the previous layout where the designators have changed, so that one can be resolved just by updating the designators in the associated design rule. Looking at the report, a lot of the other errors relate to silk screen violations, so I'll just go ahead and fix those. Let's have a closer look at the rules set up for the differential pairs. Under the differential pair routing section, the rules that were created in the schematics are shown. We can see the 4 differential pair classes that were defined in the schematics, with each having a rule that defines the impedance profile. We can check that the SDI out class uses the correct impedance profile and that the track and gap settings are as expected. Now, we can check the matched length constraint on the differential pair class. The intra-pair matching is set to a tight tolerance of 0.1 of a millimeter. But there is no requirement for inter-pair matching with these signals. Each differential pair is independent. The PCB properties can be used to check that the intra-pair length matching has been met. Selecting SDI out highlights the 8 differential pairs and displays the trace lengths in the table. Selecting a pair in the table displays the length of positive and negative traces. They are all within the required 0.1 mm tolerance. The differential pairs are closely matched because each pair has 2 bends, so the positive and negative traces are equalized. There will be a small skew between traces after the first bend, which will be corrected after the second bend. Since the traces are short, I will not adjust the trace to correct it. Differential pairs can be rounded by selecting strong glossing and round hugging style. Touching the trace now rounds the traces at each of the bends. But be careful to check that moving the trace doesn't affect the endpoints of each differential pair. Well, this concludes part 1 of this PCB design. If you are still watching, then part 2 will include a report from the PCB fabricator, and we'll take a look at the assembled PCB and review any problems or assembly difficulties. If you like this format, then please like and subscribe to receive notification of new content. Thank you.